So do we have any questions? Arnie?
Thank you for the nice talk. So maybe you have some thoughts on something I've been wondering for a while is, do you think there's some kind of algorithmic version of the thermodynamic uncertainty relation?
Um, oh, that's the, sorry, I didn't memorize by name. That, yeah, like about how you can't. So I think in my setting there isn't because I made so few assumptions that in this setting, like I don't even assume continuous time, right? So if you have like a discrete time process, you could just jump deterministically, and so there's no uncertainty there. But if you make, yeah, I think you would have to make like an additional assumption there. But I'm guessing if you make the same assumptions that you do in stochastic thermodynamics, you probably could. I haven't investigated yet. Yeah, this is the kind of thing that I think it would be great to like have an analogous theory for the algorithmic quantities.
Maybe I was actually, I think it's also interesting to think like what is the kind of algorithmic notion of fluctuations, right?
Mhm.
Because it seems very related to that. Anyway, thank you.
Sure thing. Oh, a small comment about fluctuations, I guess, is that if you transition randomly, because this on the coarse grain picture, it is just a Markov process, it is always possible to get lucky and end up at a simpler state, a lower complexity state. But I guess the claim is you can't do that with high probability. I don't know if I answered your question.
Are there other questions for Arnold? Okay, thank the speaker once again.
Thank
And
you.
Songela, are you good to go?
Yes, Aram, would you mind unsharing? Thank you. Okay. Okay,
Yep, you're up.
great. Thanks everyone for sticking around to the very last night lightning talk. I'm excited to give this talk. Thank you to the organizers for inviting me to give this talk. It's been a nice workshop so far. And also thank you to my advisor, David Limmer, and funding sources for their support. So, right, my name is Songela Chen. I'm a PhD student at UC Berkeley. And today I'll be telling you about how we are attempting to control heat dissipation from bit erasure in a realistic model of stochastic circuits. So in this audience, we are very familiar with the problem of bit erasure. One common picture is that we have a double well potential, and initially your probability density could be equally distributed on either side of this potential because your bit could have a 0 or 1 state. And then when we want to erase that bit, we want to shift all of the density into the left side well of this potential. Landauer told us that there is an energetic cost to doing this bit erasure. So there is an energetic cost associated with the information loss. But this is a quasi-static bound, and so it has limited applicability in real systems. There has been a finite time correction to this bound, which adds a term that goes inversely with the length of time that we give ourselves to achieve the bit erasure. However, this finite time correction still assumes that we have full control over the shape of this potential landscape. And in fact, in real systems, it's often not possible to simplify our picture into just a double well. There are other practical considerations, like the potential of having multiple baths that our system is connected to, the existence of a housekeeping heat that's required to power the system on continuously, and other such things. And so we want to model realistically what does an actual bit look like in our computers. So here's a cartoon of a 6-transistor static random access memory, or 6TS RAM. This circuit stores 1 bit of information as either a 0, 1 or 1, 0 across these two states. So it consists of two coupled inverters, which can take a 0 state, turn it into a 1, and vice versa. We can control the state of this bit using these effective switches that depend on what electrical engineers know as the word line voltage, which I'll call the VW. This is our control parameter for this system. And so the goal for our bit erasure in this physical picture is to use this VW control to drive our system towards the 1-0 state. Under the hood, what this CMOS architecture looks like is that we have two electrodes at fixed potential. The bias across these two electrodes is what I'll refer to, so I'll call that the bias. I might also call it the driving voltage. These electrodes are coupled to two transistors, which we model as single electron states that can be either occupied or empty. And then these transistors are connected to a capacitor, which lets us read out the state of the system. To control the state of the bit, we can connect these capacitors externally to these access transistors, which are controlled by the control parameter. So two of these comprise one 6T SRAM. In this model, our rates obey local detailed balance, so that lets us talk about thermodynamic consistency in physical units. And I'll also note that this is not the only model that's been developed of CMOS architectures, and this is one common alternative. Now, using our model, we can propagate the dynamics of our system both stochastically in the discrete state picture using kinetic Monte Carlo simulations, and that's what gives us these fuzzy colored lines on this figure. But we can also take a mean field approximation to these dynamics by taking a mean occupancy of each of these transistors, and using the mean rates, we obtain these thicker black lines overlaid on the KMC simulations. And so that gives us an actually numerically more tractable way of probing the dynamics of the system. In both pictures, we can obtain expressions for the heat dissipation, either as a log ratio of rates forward and backward, or through the current in the various channels in the system. And then the goal here is to use the mean field theory, which is numerically much more friendly and tractable, to optimize the control protocol. And here we're going to optimize the coefficients of this sine series, which forms the basis of our control time dependency. And we're going to use automatic differentiation to minimize this loss function that is a combination of the heat dissipation as well as an error metric, where the error is simply the distance between the current state of the bit and our desired 0 state. So, using this mean field optimization, our first, perhaps counterintuitive result is that dissipation is actually time extensive. So, whereas in an equilibrium picture, we think that the quasi-static limit or the reversible limit gives us the minimum dissipation process, in a non-equilibrium picture, that's not true, because we have this housekeeping heat contribution that, although it's small, it's finite, and it continues to build over the time that we have this circuit being powered on. And so in this picture, dissipation accumulates over time, and the minimum cost of bit erasure is not Landauer's bound of kBT log 2, but rather the energy required to charge and discharge these two capacitors in the 6T SRAM circuit. And so the minimum energy cost here is actually the energy we obtain from electrostatics of the capacitor. And then we can also observe that as we increase the driving voltage, or as we increase the bias across each of the gates, we get less housekeeping heat for higher biases because the higher biases are less noisy. So the housekeeping heat contribution is smaller for higher voltages. However, there's no free lunch. And so we find that the lower dissipation at very short times comes at the cost of a very high error, meaning that most of the time the bit is not successfully erased. So whereas there is this increase in dissipation with the length of the protocol, there's a decrease in the error with the length of the protocol. And so this implies that there's an optimal regime where dissipation is still relatively low, but the error is acceptably low as well. So again, higher biases gets us closer to this optimal, this minimum cost, which I've denoted with the dashed lines corresponding to each bias, each level of the driving voltage. And so we can see this optimal trade-off. Putting these two figures together, we can obtain a Pareto front of this dissipation versus accuracy trade-off. These two figures show the same data, but the right-hand side is normalized to the energy of the capacitor at that driving voltage. So once again, we see that there is a higher absolute dissipative cost at short times for higher driving voltages or higher biases. But that's offset by the fact that higher biases give you lower error. So the darker lines give you lower error to the left of this plot. I mentioned earlier that there have been alternative models developed for CMOS architectures, and this paper has shown similar results in a different model. Okay, so I've told you that we developed a physically realistic model of a 6T SRAM circuit that we can control with time. This realistic model can be optimized using a mean field theory that is numerically tractable. And we've seen using this mean field optimization that dissipation is time extensive and that we obtain a trade-off between the amount of heat dissipated and the level of error or accuracy in this bit erasure. So hopefully I'll put out a paper on these results in the next month or so, but in the meantime, thank you for your attention and I'll be happy to take any questions.
All right, thank